Hello, we are going to talk about modern algebra today, and we're going to talk about counting automorphisms. So last time we talked about automorphisms that fix the base field, and this time we're going to figure out how many there are given an extension of fields. So if we have an extension of fields, f contained in K, the set of all possible automorphisms from K to K that fix the base field F is called the Galois group. Now we haven't talked about what a group means yet. That's going to be the next chapter that we talk about, chapter 15 in our book. And it's been a long time, but we did have a little exposure to Galois. Early on in the course, you read some stuff about Galois' contributions. And assuming I get this to work right, you should be able to click right here to read more. So when we're talking about the Galois group of K over F, we denote it in this particular way, gal of K over F. And let's look at our favorite example here. We have the conjugation automorphism from R join I to itself. And we saw before that it's an automorphism, which means it's an element of the Galois group of the complex numbers over R. And so is the identity automorphism. That's always in there because it fixes everything, including the stuff we adjoined. Here's another example. Let's look at the Galois group of Q adjoined zeta 3 over Q. Now, we know that we're going to look at the automorphisms of Q adjoined zeta 3 to Q adjoined zeta 3 that fix the rational numbers, which means we just need to figure out where we're sending zeta 3. And we know that we have to send zeta 3 to a root of the minimum polynomial of zeta 3, which is x squared plus x plus 1. All right, so we don't have that many choices here. The possible roots of this thing are in Q adjoined zeta 3 are zeta 3 or zeta 3 squared. And so the possible automorphisms either send zeta 3 to itself or they send zeta 3 to zeta 3 squared. And zeta 3 to itself is just the identity automorphism for this thing. So the Galois group here of Q adjoined zeta 3 over Q, when we look at its size, it has two different automorphisms. Up above we named them F and G. And now let's observe something pretty rad here. The size of this Galois group, which is 2, is also the dimension of Q adjoined zeta 3 over Q as a vector space, and it's also the degree of the minimum polynomial of zeta 3 over Q. And now it's time for a bad math joke. Why couldn't the base field have puppies? Because it was fixed by an automorphism. So let's say that we have a Galois group and we want to understand what automorphisms do. Well, that's what this proposition tells us about. If F is an element of the Galois group of F adjoin A1 through AN over F, then F is uniquely determined by what it does to A1 through AN. That means that we get some values in F of A1 through AN, and we assign them to our automorphism. So all we need to know is what happens to the stuff that we adjoined. How do we shuffle it around? And that's pretty good news because that gives us a way to understand our automorphisms, like our conjugation automorphism, right? We adjoined I, and all we needed to know was that C of I was negative I. And in our last example, Q adjoined zeta 3, our automorphisms depend only on where zeta 3 gets sent. And that leads us to proposition 14.8. So if F is a subfield of the complex numbers and P of X is a polynomial in F bracket X, then the Galois group of the fixed field of that polynomial over F is the dimension of the vector space F with the roots of P of X over F, right? So the number of automorphisms is precisely the dimension of a vector space. That's awesome, but there's a big warning here. In general, if we have an extension of fields K over F, we don't necessarily have that the size of the Galois group is the dimension of that vector space. there has to be a polynomial that links K and F in order for the dimensions to give us the size of the Galois group, right? We've got to have P of X in F bracket X, where K is the fixed field of P of X. All right, time for an example. We are going to look at the Galois group of Q with the roots of x to the fourth minus 3 over Q. And we're going to let R be the fourth root of 3. So that's one of the roots of this thing. Now, if we think about the roots of the polynomial x to the fourth minus 3, our roots are r times zeta 4, r times zeta 4 squared, and r times zeta 4 cubed. And if we remind ourselves that zeta 4 is actually I, we get r, ri, negative r, and negative ri. So to figure out what our extension field is here, we have the roots of P of X adjoined with Q give us just Q adjoin R and I. Now, to find the Galois group of our extension of fields here, we just need to figure out where the R and I that we adjoined are going to go. Right, so we're going to look at automorphisms from Q adjoin R, comma I to itself that fix Q. So, in order to start, it's useful to know how many we're looking for, and because of our last proposition, we can check the dimension here. Well, the dimension is going to be the dimension of Q adjoin R and I over Q. And so I'll make a field extension diagram to figure out how this works. So x to the fourth minus 3, that's irreducible over Q by Eisenstein's criterion with prime 3, and so we get that the dimension of Q adjoin R over Q is 4. And x squared plus 1 is irreducible over Q adjoin R by proposition 8.12, and so that has dimension 2. And we have that the dimension is multiplicative, so we get that 4 times 2 is 8, and Q adjoin Ri is dimension 8 over Q. Now, we could go the other way, but we don't have Eisenstein's criterion over Q adjoin I, but we do know that every basis has the same size, so we could figure out that the degree of that extension is 4. And that's a cool trick. You'll actually play with that in your homework. All right, so Q adjoin R and I over Q has dimension 8, right? That's 2 times 4. Yes, I know you're very excited that you're paying Hamilton money to see that 2 times 4 is 8. But it's a vector space dimension thing, right? To get a basis, we would just kind of cross multiply the bases, and we get a basis for Q adjoin Ri over Q. So we've got to find 8 automorphisms. And proposition 14.8, our last proposition, said we just need to know where R is going to go and where I is going to go. And if we find all the possible ways we can assign those, we should come up with 8 automorphisms. Now, R and I have to go to roots of their minimum polynomials over Q. So we just need to remind ourselves what those are. F of R is in the set R, Ri, negative R, and negative Ri. And F of I is either plus or minus I, right? Because those are the roots of x squared plus 1. We'll put all of this together in an automorphism table, right? We're going to just kind of mix and match all the possible ways we can assign R and I. There are 4 choices for R, 2 choices for I, and so we get 8. Here is what an automorphism table looks like. On the top, labeling the columns, we're going to have automorphisms, and I'll give them names. They'll be F1 through F8, so I'm looking for 8 automorphisms here. And then I'm thinking about the radicals that I adjoined, right? Like I adjoined R and I adjoined I. So F1 can be the identity automorphism that sends R to I and I to itself. Maybe by the time we get to F4, we think, oh, okay, we're going to send R to negative Ri, but I still going to go to itself. And F6 sends R to Ri and I to negative I. These are all the possible ways that we can mix and match our places that we can send R and I in a table. And so this completely describes for us what these 8 automorphisms look like. And that's great news for us because if we wrote it out in general, we know that Q adjoin Ri, an arbitrary element of that is terrible, right? It looks like A1 plus B1R plus C1R squared plus D1R squared. Then we write the same thing over, but now we've got an I attached to it. And all of those A's and stuff, the A1 through D2 are elements of Q. And normally we'd have to figure out what does F4 do to a general element, and that's gross. But if we remember how our automorphisms work, we just break apart multiplication and addition, and we get F4 of A1 plus F4 of B1 times F4 of R, blah, 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 blah. And remember that this automorphism fixes Q. So all the A's, B's, C's, and D's go back to themselves. And to figure out what happens to R and what happens to I, we just look in our table, right? So F4 of R is negative Ri, and F4 of I is I. And so we fill those in and we simplify and we collect like terms, and we see that we get an element back in Q adjoin R and I. But we don't want to do this in general. That's why we like the table. The table is a nice labor-saving device that completely describes everything we need to know if we need to apply the automorphism to something, but we don't actually need to write it out generally. So here's one more example. We're going to find all the elements of the Galois group of Q adjoin cube root of 11 and zeta 3 over Q. Now, we're keeping in mind our warning. Is Q adjoin cube root of 11 zeta 3 the fixed field of some polynomial? Well, as it happens, yes. It's the fixed field of x cubed minus 11, because we can build all the roots of that polynomial out of these things that we're adjoining. Woo! But if it's not the fixed field of some polynomial, we have to do something else because of our warning. Okay, so we're going to have the dimension of the fixed field over Q elements in this Galois group. And we'll build another little extension tower here. So we're going to throw in cube root of 11 and zeta 3. And we do this over cube root of 11, and we do that over Q. Well, cube root of 11 has minimum polynomial x cubed minus 11 by Eisenstein, and we know zeta 3's minimum polynomial is 2. And so we're going to have 6 total automorphisms. 2 times 3 is 6. So we make our little automorphism table with F1 through F6, and we figure out where we're going to send cube root of 11 and zeta 3. Well, cube root of 11 has to go to cube root of 11 zeta 3, or cube root of 11 zeta 3 squared. Those are the possibilities. And while cube root of 11 is deciding where to go, zeta 3 either goes to itself or to zeta 3 squared. And that is a pretty complete description of the automorphisms in our Galois group. Complete enough for homework and for writing assignments. All right, see you next time. Happy fixing!